On March 14th, 1949, roughly 70 people gathered at the Institute for Advanced Study in Princeton, New Jersey, to celebrate Albert Einstein's 70th birthday. Einstein was already the most famous scientist alive, probably the most famous scientist who had ever lived, and he had spent the last several decades watching the world both worship and misunderstand his work. Relativity had been absorbed into culture as a vague metaphor for everything is relative. E equals mc squared was printed on coffee mugs and t-shirts. People who could not tell you what the C stood for would confidently invoke the equation in cocktail party arguments about subjectivity. Einstein was tired, but there was one person at the Institute whose understanding of Einstein's work was not vague, not metaphorical, not decorative. A quiet, painfully thin Austrian logician named Kurt Godel. And for Einstein's 70th birthday, Godel gave him a gift. The gift was a 4-page paper published that July in the Reviews of Modern Physics, Volume 21, Issue 3, pages 447 through 450. 4 pages. In those 4 pages, Godel demonstrated that Einstein's own equations, the field equations of general relativity, the very equations that describe how mass curves spacetime permit closed time-like curves, paths through spacetime that loop back on themselves, trajectories that a physical object could follow and arrive at its own past. Time travel, not as science fiction, not as speculation, as a mathematical consequence of the most successful theory of gravity ever written. Einstein read the paper. He understood it immediately, and it disturbed him for the remaining 6 years of his life. This is a story about whether the laws of physics forbid time travel. The answer, as of today, is that nobody knows. And the reason nobody knows is not that the question is too hard to investigate. It is that every investigation points in 2 directions at once. The mathematics says yes, time travel is permitted. The universe seems to say no, or at least not yet. And the gap between those 2 answers is exactly where the deepest unsolved problems in physics live. To understand why, you need to understand the friendship, because this was not some obscure physicist sending a provocative paper to a famous name. This was Einstein's closest friend telling him that his own theory contained something Einstein had never wanted it to contain. Godel arrived at the Institute for Advanced Study in 1940. A refugee, he had fled Nazi Austria by an almost absurd route, traveling east across Russia on the Trans-Siberian Railway, then through Japan, then by ship to San Francisco, and finally cross-country to Princeton. He was 34 years old, already the author of what may be the most important result in the history of mathematical logic, the incompleteness theorems, published in 1931 when he was 25. The incompleteness theorems proved that any consistent mathematical system powerful enough to describe arithmetic will contain true statements that cannot be proven within the system. Mathematics cannot fully validate itself. It was the kind of result that ends careers in philosophy and starts them in logic, and Godel had done it before his 26th birthday. By the time Godel reached Princeton, Einstein was 61. He had spent the last 2 decades searching for a unified field theory, mostly alone, increasingly out of step with the quantum revolution that his own early work had helped spark. The 2 men found each other almost immediately. They began taking daily walks together, to and from the Institute, through the quiet, residential streets of Princeton. An unnamed member of the Institute later described it simply. They did not want to speak to anybody else. They only wanted to speak to each other. Think about what that friendship looked like from the outside. Two European exiles, both refugees from fascism, walking slowly through suburban New Jersey, speaking German, arguing about the nature of time and truth. Einstein was worn, rumpled, famous, perpetually half amused. Godel was gaunt, precise, suspicious of nearly everything, and terrified of being poisoned. They were nothing alike temperamentally, but intellectually, they were the only two people in each other's vicinity who operated at the same altitude. Einstein later told his friend and colleague Oscar Morgenstern, near the end of his life, that his own work no longer meant much to him, that he came to the Institute merely, and these are the words Morgenstern reported, to have the privilege of walking home with Godel. The most famous physicist in history said the main reason he went to work was to walk home with a logician. There is a story about those walks that tells you everything about both men. In late 1947, Godel applied for United States citizenship. Einstein and Morgenstern agreed to accompany him to the hearing as witnesses. In the weeks before the exam, Godel prepared with his usual terrifying thoroughness. He studied the Constitution, and he found a logical inconsistency in it, a structural flaw that he believed could, in principle, allow the United States to legally become a dictatorship. Einstein was alarmed, not because Godel was wrong, but because Godel was exactly the kind of person who would explain this discovery to a federal judge during a citizenship hearing. On December 5, 1947, the three men drove to Trenton. In the car, Einstein reportedly told jokes the entire way, trying to distract Godel. It did not work. When the judge, Philip Foreman, asked Godel if he believed the kind of dictatorship that had taken over Germany and Austria could happen here, Godel said yes, and began to explain why. The judge, to his eternal credit, cut him off and moved the proceedings along. Godel became a citizen. That was who Godel was, a man who could find the flaw in the United States Constitution and feel compelled to report it at the worst possible moment. A man who could not leave a logical gap unpursued, no matter the social consequences. And in 1949, 2 years after the citizenship hearing, Godel turned that same relentless precision on Einstein's own theory and found something no one had expected. The paper Godel published, titled An Example of a New Type of Cosmological Solutions of Einstein's Field Equations of Gravitation, describes a universe that satisfies Einstein's field equations perfectly. Every mathematical requirement is met. The solution is exact. But the universe it describes is rotating, not objects within it rotating, the entire universe rotating as a whole, uniformly, everywhere. And in that rotating universe, the geometry of space-time is so severely twisted that closed time-like curves pass through every single event, not some region, not near some exotic object. Every point in the space-time lies on a closed time-like curve. Every event in the Godel universe can be reached from its own future. A closed time-like curve is exactly what it sounds like. In general relativity, your path through space-time is called a world line. Time advances along your world line. Normally, your world line moves forward, always forward, from past to future. A closed time-like curve is a world line that bends so severely that it loops back and reconnects with itself. It is a circle in time. You start at a particular moment, travel forward along your world line, and arrive back at the exact moment you started. You have not traveled faster than light. You have not violated any local law of physics. The space-time itself is curved in such a way that forward is eventually backward. What that means concretely is this: a traveler in Godel's universe could board a rocket, follow a precisely calculated trajectory through space-time, and arrive back at the same place and the same time they departed. They could attend their own launch. They could, if the trajectory were different, arrive before their own launch. They could visit their own past. Now, you might immediately want to object. Our universe does not rotate like that. Stephen Hawking investigated exactly this question in 1969 and found no observational evidence of the kind of large-scale rotation Godel's solution requires. The cosmic microwave background, the distribution of galaxies, the expansion of the universe, none of it shows the signature of a Godel-type rotation. So you might want to say, fine, interesting mathematical curiosity, but irrelevant to us. There is another thread to Godel's life that needs planting here, because it will matter later. After his close friend, Moritz Schlick, the philosopher who had founded the Vienna Circle, was murdered by a student on the steps of the University of Vienna in 1936, something shifted in Godel. He developed an obsessive fear of being poisoned. The fear was not rational, and Godel, the most rational man alive, knew it was not rational. But knowing did not help. Over the years, the fear intensified. He would only eat food that had been prepared and tasted by his wife, Adele. Adele Godel, born Adele Porkert, was a former nightclub dancer, 6 years older than Kurt, divorced before she met him. His family had disapproved of the marriage, which took place on September 20th, 1938. She was nothing like him. She was vivacious where he was withdrawn, practical where he was abstract, socially fluid where he was socially paralyzed. And she was, quite literally, the only person on earth he trusted enough to eat food she prepared. His favorite movie, incongruously, was Snow White and the Seven Dwarfs. His diet, in later years, would narrow to butter, baby food, and laxatives. Remember that. It becomes important. Godel anticipated that objection, and his response is the reason the paper disturbed Einstein so deeply. Godel's point was never that our universe rotates. His point was that Einstein's equations do not prevent time travel. The equations of general relativity are supposed to describe the fundamental laws governing space-time. If those laws are correct, and they are the most precisely tested theory in all of physics, then any universe those laws permit tells us something about what the laws allow. And what Godel showed is that the laws allow time travel, not in some edge case, not in some contrived scenario that bends the rules, in a perfectly valid, mathematically rigorous solution to the field equations. The implication is devastating. If the same fundamental laws that govern our universe also govern a universe where time loops back on itself, then those laws do not protect the flow of time. The fact that our particular universe might not contain closed time-like curves is an accident of initial conditions, not a consequence of fundamental physics. It is like discovering that the laws of chemistry permit a molecule that could dissolve any container, even if that molecule does not happen to exist naturally on Earth. You now know the laws of chemistry do not prevent it. and that changes what the laws of chemistry mean. Godel was not primarily interested in time travel as a practical matter. He was a philosopher of mathematics, not an engineer. What he wanted to prove was something far more radical. He wanted to prove that time is not real. His philosophical argument, laid out in a companion paper titled A Remark About the Relationship Between Relativity Theory and Idealistic Philosophy, published the same year, goes roughly like this. If time travel is possible in any universe consistent with the fundamental laws, then the passage of time, the sense that the past is fixed, the future is open, and we move through the present, is not a feature of reality. It is a feature of our experience. The laws do not mandate it. And if the laws do not mandate it, then what we call time is something closer to an illusion than a physical fact. This connects to one of the deepest questions in philosophy. Is the past gone? Is the future unwritten? Or do past, present, and future all exist simultaneously, spread out like a landscape, with our consciousness merely moving through it like a spotlight? Philosophers call the first view presentism, the idea that only the present moment is real. The second view is called eternalism, or the block universe, the idea that every moment in time is equally real, and the flow of time is an illusion produced by consciousness. Godel was arguing for eternalism, everything already there. Time as a dimension you can move through in any direction, just like space. Our experience of time flowing is real, in the way a dream is real while you are dreaming it, but it does not reflect the fundamental structure of reality. We experience time as flowing. We feel the past receding. We feel the future approaching. But if Godel is right, that experience is no more fundamental than the experience of the sun rising. The sun does not rise, the earth rotates, and time does not flow. We move through it, or perhaps more accurately, our consciousness illuminates successive slices of a static four-dimensional block. The slices feel like moments. The illumination feels like the passage of time, but the block is just there, all of it, always. Einstein read this. Einstein, who had already shown that simultaneity is relative, that time runs differently depending on your velocity and your gravitational field, who had already dismantled the Newtonian idea of absolute time. Even Einstein found Godel's conclusion unsettling. He wrote, in a response published in the same volume where Godel's philosophical paper appeared, about the implications of what he called a closed causal series. He noted that if such solutions exist, then the distinction between earlier and later is abandoned for world points which lie far apart in a cosmological sense. Einstein in 1952 told Morgenstern that Godel's paper was one of the most important on relativity since his own original paper appeared. So here is where we stand, at the end of this first thread. The greatest logician of the 20th century used the greatest physicist's own equations to prove that time travel is mathematically consistent with the laws of physics. The greatest physicist acknowledged this was important and correct, and nobody from 1949 to today has been able to dismiss it. But our universe does not rotate like Godel's universe. So maybe this is just a mathematical curiosity, a theoretical possibility with no practical relevance. Maybe Einstein's equations are more permissive than reality, and there is something else, some other law, some deeper constraint that prevents closed, time-like curves from actually forming. To find out, we need to look at whether Godel's solution was a one-time fluke, or whether closed, time-like curves keep showing up in general relativity. And the answer to that question is the answer that nobody wanted. They show up everywhere. The first person to write down a solution to Einstein's equations that contained closed, time-like curves was not actually Godel. It was a Dutch physicist named Willem Jacob van Stockum. In 1937, 12 years before Godel's paper, van Stockum solved the equations for the space-time around an infinitely long, rotating cylinder of dust. His solution was mathematically correct. It was published, it was read, and nobody, including van Stockum himself, noticed what it contained. Van Stockum was not looking for time travel. He was studying rotating matter distributions in general relativity. The CTCs were an unintended byproduct of a routine calculation. At a critical radius around van Stockum's cylinder, the rotation of the dust drags space-time around with it so severely that a light ray emitted at that radius loops all the way around and returns to its starting point. Move further out to a second critical radius and something worse happens. A light ray returns not just to the same point in space, but to the same point in space-time. It arrives before it left. That is a closed, time-like curve, and it was sitting there in van Stockum's published mathematics for 12 years before Godel made the concept explicit. Even earlier, in 1924, the Hungarian physicist Cornel Lanzos had found related rotating solutions to Einstein's equations that also contained what we would now recognize as CTCs. He did not recognize them either. What this tells you is that closed time-like curves are not some exotic feature that Godel cleverly engineered into the equations. They are a natural consequence of rotation in general relativity. They were hiding in plain sight for decades. Multiple independent physicists kept stumbling over them without realizing what they had found. After Godel made the concept explicit, other physicists started looking, and they kept finding more. In 1974, Frank Tipler at the University of Maryland published a paper titled Rotating Cylinders and the Possibility of Global Causality Violation in Physical Review D. Tipler took van Stockum's rotating cylinder and pushed it to its logical extreme. He showed that if you had an infinitely long cylinder of sufficient mass, more than 10 times the mass of the Sun, with density approaching that of a neutron star, spinning at billions of revolutions per second, the space-time around it would be so dramatically warped that light cones tip over. In normal space-time, your future light cone points forward in time. Near Tipler's cylinder, the light cones tilt so far that the forward direction in time becomes a direction that loops backward. A spacecraft flying a carefully calculated helical path around the cylinder could follow a closed, time-like curve and arrive in its own past. The problem with Tipler's cylinder is the word infinitely. The proof only works for a cylinder of infinite length. Tipler suggested that a finite cylinder might also work if it spun fast enough, but he could not prove it. Hawking later argued that a finite Tipler cylinder would need negative energy, so-called exotic matter, to produce CTCs, which partially defeats the purpose, since Tipler's main selling point was that his cylinder used only ordinary matter. But the Tipler cylinder is not the most unsettling example. That distinction goes to the Kerr black hole. In 1963, the New Zealand mathematician Roy Kerr found the exact solution to Einstein's equations for a rotating, uncharged black hole. This was a breakthrough of enormous significance because real black holes almost certainly rotate. Matter swirling into a black hole carries angular momentum, which means the black hole spins. The Kerr solution is not a theoretical curiosity. It describes objects that actually exist in our universe. We have observed them. We have photographed their shadows. The Kerr metric describes a black hole with two event horizons. The outer horizon, called R+, is the boundary most people think of when they picture a black hole. Cross it, and you cannot escape. But there is a second, inner horizon, called R-, or the Cauchy horizon. And below that inner horizon, in the deep interior of a rotating black hole, the Kerr solution contains closed time-like curves. They are there, in the mathematics, of real objects. The interior of the Kerr black hole also contains something bizarre. The singularity is not a point, as it is in a non-rotating black hole. It is a ring singularity, and a particle, in principle, could pass through the center of the ring without touching the singularity and find itself in a region of space-time where CTCs exist, where time loops back on itself. Some solutions even suggest the particle could emerge into a completely different region of space-time, a kind of one-way trip to somewhere else entirely. The reason this is particularly unsettling is that the Kerr solution is not some theorist's fantasy. It describes the space-time around every rotating black hole in the universe. The black hole at the center of our own galaxy, Sagittarius A star, with its 4 million solar masses, is almost certainly described by the Kerr metric in its exterior. The black hole M87 star, the first one ever directly imaged by the Event Horizon Telescope in 2019, is a Kerr black hole. If you take the Kerr solution at face value, every rotating black hole in the cosmos has closed time-like curves hiding in its interior. Now, before you start planning a trip, there is a serious complication. Most physicists believe the inner Cauchy horizon of a Kerr black hole is violently unstable. Any matter or radiation falling into the black hole piles up at the Cauchy horizon, creating what is called a mass inflation singularity. The energy density grows without bound as you approach the inner horizon. This almost certainly destroys the CTC region before anything could reach it. The interior of the Kerr solution, including the closed time-like curves, probably does not survive contact with the real universe. But notice the word probably. It has not been proven. The instability of the Cauchy horizon is well supported by calculations, but those calculations are not complete. They are done in the semi-classical approximation, which means they combine classical general relativity with quantum field theory in a way that we know breaks down at extreme conditions. The same caveat that will follow us through this entire story. The final answer requires a theory of quantum gravity, and we do not have one. In 1991, Richard Gott III at Princeton published yet another CTC solution. This one involved cosmic strings, hypothetical one-dimensional defects in space-time that might have formed during phase transitions in the very early universe. A single cosmic string cuts a wedge-shaped deficit angle out of the space around it. Two infinitely long cosmic strings passing each other at nearly the speed of light would warp space-time so dramatically that a spacecraft flying the figure-8 pattern around them could travel into its own past. Once again, the mathematics checks out. Once again, The requirements are absurd. Infinitely long strings, relativistic speeds. No cosmic strings have ever been observed. There is a pattern forming, and it is worth stating plainly. Every time a physicist sits down and solves Einstein's equations for a situation involving sufficient rotation or sufficient mass energy, closed time-like curves appear. They are not rare. They are not anomalies. They are a recurring feature of general relativity. The theory keeps producing them. Van Stockham found them. Godel found them. Tipler found them. Gott found them. They appear in the interiors of rotating black holes, around spinning cylinders, between moving cosmic strings, in rotating universes. The equations do not merely tolerate time travel. They seem to invite it. It is as if you kept solving the equations of fluid dynamics, and every solution produced whirlpools. At some point, you would stop calling whirlpools anomalies and start asking whether the equations are telling you something fundamental about how fluids behave. That is the situation with closed time-like curves and general relativity. They are not bugs. They might be features, but every single solution has a catch. Godel's universe requires global rotation we do not observe. Van Stockham and Tipler need infinite cylinders. Kerr's CTCs are probably destroyed by the instability of the inner horizon. Gott strings are infinitely long and unobserved. The pattern is consistent. The math says yes. The engineering says you cannot get there from here. And then, in 1985, a novelist called a physicist, and everything changed. Carl Sagan was writing a novel called Contact. It was science fiction, but Sagan wanted the science to be real. His protagonist, Dr. Ellie Arroway, needed to travel across the galaxy quickly, and Sagan had originally written her entering a black hole and emerging light years away. He knew this was hand-waving, so he called his friend Kip Thorne at the California Institute of Technology and asked if there was a better way. There is something worth pausing on here. A science fiction novelist called a physicist for a plot point, and the answer to that phone call launched an entirely new subfield of theoretical physics. Thorne did not treat Sagan's question as trivial or recreational. He recognized that the question, what kind of shortcut through space is actually permitted by general relativity, was a real physics question that had not been adequately addressed. The fact that a novelist asked it first says something about how the boundaries of physics sometimes advance, not always through systematic research programs, but sometimes through a question nobody thought to formalize. Thorne is one of the most distinguished relativists of the 20th century, born June 1st, 1940, in Logan, Utah. He spent most of his career as the Feynman Professor of Theoretical Physics at Caltech. He would later co-found LIGO, the Laser Interferometer Gravitational Wave Observatory, which detected gravitational waves for the first time on September 14th, 2015, a discovery that won Thorne, Rainer Weiss, and Barry Barish the Nobel Prize in Physics in 2017. He was also the scientific consultant on Christopher Nolan's Interstellar. But in 1985, all of that was still in the future. What Thorne had was deep expertise in general relativity and a willingness to take a novelist's question seriously. Thorne told Sagan a black hole would not work. Anything falling through the event horizon of a black hole is trapped and destroyed. There is no coming out the other side. But Thorne had another idea. What if, instead of a black hole, you used a wormhole? a tunnel through space-time connecting two distant regions. Wormholes had been discussed theoretically since the 1930s, when Einstein and Nathan Rosen described what are now called Einstein-Rosen bridges. But those early wormholes were not traversable. They pinched off too quickly for anything to pass through. Thorne asked a different question. What if an infinitely advanced civilization could engineer anything that is not forbidden by the laws of physics? Could they build a wormhole that stays open long enough to walk through? He and his student Michael Morris worked out the mathematics. The answer was yes, but with a condition. The wormhole's throat, the narrow passage connecting the two mouths, would collapse under its own gravity unless something held it open. That something would need to have a very unusual property. It would need to have negative energy density. Energy that is, in a precise technical sense, less than nothing. Matter or energy that gravitationally repels rather than attracts. This is what physicists call exotic matter. Morris and Thorne published two landmark papers in 1988. The first, in the American Journal of Physics, laid out the traversable wormhole concept. The second, in Physical Review Letters, with the addition of Ulvi Yurtseva, explored the implications for time travel. Because Thorne and his colleagues realized something remarkable. A traversable wormhole is not just a shortcut through space. It can be turned into a time machine. The method is almost shockingly simple. Start with a wormhole. Two mouths, call them A and B, initially synchronized in time. Now accelerate mouth B to near the speed of light, then bring it back. Or place it near a very massive object, like a neutron star or a black hole. Either way, special or general relativistic time dilation means mouth B experiences less time than mouth A. When you bring them back together, mouth B is younger than mouth A. There is now a time difference between the two ends of the wormhole. Here is where it gets strange. The interior of the wormhole still connects the two mouths directly. The tunnel does not care about the time difference. So if mouth A reads Tuesday at noon and mouth B reads Monday at noon, because of the time dilation it experienced, then walking into mouth A on Tuesday at noon means walking through a tunnel that connects to mouth B at Monday at noon. You enter on Tuesday, you exit on Monday. You have traveled 24 hours into the past. Igor Novikov, the Russian physicist, independently realized the gravitational version of the same idea around the same time. Place one mouth of a wormhole near a massive body, let time dilation create the offset, and you have a time machine. This was different from everything that came before. Godel's rotating universe was a cosmological solution, a whole universe with special properties. Tipler's cylinder required infinite length. Gott's strings were cosmic scale. But a wormhole time machine is a local object. It is something you could, in principle, build. Not with current technology, not with anything close to current technology, but the obstacles are engineering obstacles, not fundamental prohibitions. The Morris-Thorne wormhole was the first CTC proposal that looked even remotely like a blueprint. Sagan adopted the idea for contact. In the novel, an advanced alien civilization maintains a network of wormholes for interstellar transit, built so long ago that even they have forgotten who originally constructed them. The exotic matter technology comes from an even older, now vanished, civilization. The novel was published in 1985. The movie starring Jodie Foster came in 1997. But for physicists, the novel was a footnote. The real story was the papers, because once Morris and Thorne showed that a traversable wormhole could serve as a time machine, the question stopped being, does general relativity permit time travel? Godel had answered that in 1949. The question became something far more pointed. Does anything actually prevent time travel from happening? Is there a law, a principle, a mechanism, some deep structural feature of the universe that takes the mathematical possibility of CTCs and renders it physically impossible? Or is the universe genuinely open to the idea? The catch, of course, is exotic matter. Negative energy density. No known macroscopic substance has this property. In everyday physics, energy is always positive or zero. You can have a kilogram of mass, which by E equals mc squared represents an enormous positive energy. Or you can have an empty vacuum, which in classical physics has zero energy. But negative energy? Less than nothing. Except the vacuum is not really empty. Quantum field theory tells us that the vacuum is a roiling sea of virtual particles constantly flickering in and out of existence. And in 1948, the Dutch physicist Hendrik Casimir predicted something strange. If you take two uncharged, perfectly conducting metal plates and place them very close together in a vacuum, they will attract each other, not because of any electromagnetic force between them, but because of what is happening in the vacuum between them. This is one of those predictions that sounds like it should be wrong. Two metal plates in a vacuum with no charge, no current, no nothing should just sit there. There is no obvious reason for them to attract. But Casimir's reasoning was precise. Between the plates, the geometry is constrained. Only virtual photon modes with wavelengths that fit between the plates can exist there. Outside the plates, all wavelengths are possible. This means there are fewer quantum fluctuations between the plates than outside them. The energy density between the plates is lower than the energy density of the surrounding vacuum. And since the surrounding vacuum defines the 0 point, the energy between the plates is technically negative. Negative energy density. The very thing a wormhole requires. The Casimir force per unit area follows a precise formula involving pi squared, Planck's reduced constant, the speed of light, and the inverse fourth power of the plate separation. Steve Lamoureux at the University of Washington performed the first precision measurement of this force in 1997 and confirmed the prediction to within 5%. The Casimir effect is real. Negative energy density exists, but the amounts are vanishingly, laughably small. At a plate separation of 10 nanometers, the Casimir pressure is roughly 1.3 pascals. That is about 100,000th of atmospheric pressure. To hold open a wormhole of any useful size, you would need negative energy on the order of stellar masses. The gap between Casimir level negative energy and wormhole level negative energy is not like the gap between a flashlight and a searchlight. It is like the gap between a flashlight and all the light emitted by every star in the observable universe combined. Matt Visser later showed ways to minimize the exotic matter requirements, but even his optimized wormholes needed fantastical amounts. So the Morris-Thorne wormhole gave us something new. For the first time, we had a local, finite-sized, in-principle buildable time machine. But it required a substance that exists only in quantum trace amounts, and the quantities needed are preposterously beyond anything achievable. Every previous CTC solution had its own impossibility. Godel needed a rotating universe. Tipler needed an infinite cylinder. Now Thorne needed exotic matter. The central question is getting sharper. Closed time-like curves keep appearing in general relativity. Every solution that produces them requires something the universe seems reluctant to provide. But reluctant is not the same as forbidden. Nobody has proven that macroscopic amounts of exotic matter are impossible. Nobody has proven that the Cauchy horizon instability definitely destroys the interior of Kerr black holes. Nobody has proven that there is not some other, as yet undiscovered way to create CTCs. And this is the point where most popular accounts of time travel get the story wrong. If you ask a non-physicist what the main objection to time travel is, they will almost certainly say the grandfather paradox. Go back in time, kill your grandfather before your parent is born, and you can never be born to go back in time to kill him. A logical contradiction. People assume this is what stops physicists from taking time travel seriously. It is not. The grandfather paradox is a problem of logic. Physicists have solved it multiple times in multiple ways. The real obstacles are physical, not logical. Physicists are far more concerned about the energy conditions, the question of whether exotic matter can exist in macroscopic quantities, and the question of chronology protection. Can the universe actually permit the formation of a region of space-time where time loops back on itself? That is a question about the structure of space-time, about quantum fields, about what happens at the Planck scale. It is incomparably harder than the grandfather paradox, and it has not been answered. So if the math keeps producing closed, time-like curves, and the engineering obstacles are severe but not provably insurmountable, maybe what we need is someone to prove that CTCs are impossible, not impractical, impossible. Someone to demonstrate that the laws of physics contain a deep, fundamental prohibition against the formation of closed, time-like curves. Not an engineering argument about exotic matter or infinite cylinders. A proof at the level of fundamental law that the universe does not allow time to loop back on itself. Someone to close the question for good. In 1992, Stephen Hawking tried. Hawking and Thorne had been circling each other on this question for years. They were friends and intellectual rivals, two of the most creative minds in gravitational physics, and they disagreed profoundly about whether the universe permits time machines. Thorne, having constructed the wormhole time machine, maintained that the question was open. He would eventually conclude that all time machines are likely to self-destruct the moment they are activated. But he always added that this was an expectation, not a proof. Hawking was more categorical. He believed the universe contained a deep prohibition against closed, time-like curves, and he set out to find it. The paper was titled Chronology Protection Conjecture, published in Physical Review D, Volume 46, Issue 2, pages 603 through 611, submitted September 23, 1991, published July 15, 1992. And right there in the title is the word that matters most: conjecture. Not theorem, not proof. Conjecture. A conjecture is a statement a physicist believes to be true but cannot prove. Hawking had been watching the developments around the Morris-Thorne wormhole with something between fascination and alarm. After the wormhole time machine papers, Hawking and Thorne had made a bet about whether physics ultimately allows time machines. Hawking bet against. Thorne kept the question open. But bets are not proofs. And Hawking wanted something more rigorous. His conjecture states, in its most concise form, that the laws of physics do not allow the appearance of closed, time-like curves. And in the paper, he offered one of the most memorable lines in the history of theoretical physics. It seems that there is a chronology protection agency which prevents the appearance of closed, time-like curves and so makes the universe safe for historians. The Chronology Protection Agency was a playful, science fiction reference, the kind of thing Hawking loved. But the physics behind it was deadly serious. Hawking's argument went roughly like this. Consider any spacetime that is about to develop closed, time-like curves before the CTCs actually form. There is a boundary called the chronology horizon, or Cauchy horizon. It is the edge of the CTC-free region, the last surface before time loops become possible. Hawking argued that quantum vacuum fluctuations, the same kind of fluctuations responsible for the Casimir effect, would pile up at this chronology horizon. Virtual particles, normally short-lived and inconsequential, would circulate around nearly closed time-like curves near the horizon, gaining energy with each pass. The energy density of these fluctuations would grow without bound as the chronology horizon approached, and that divergent energy would warp space-time so severely that the chronology horizon itself would be destroyed or transformed into a singularity before any CTC could form. The time machine would destroy itself at the moment of activation. This was not just Hawking's intuition. The mathematics supported it, at least partially, in the semi-classical approximation, where you treat space-time classically but allow quantum fields to propagate on it. The expectation value of the quantum stress energy tensor does indeed diverge at the chronology horizon. In 1997, Bernard K., Marek Radzikowski, and Robert Wald proved this rigorously. The semi-classical energy blows up. The time machine, it seemed, could not survive its own activation. Hawking offered additional evidence, characteristically tongue-in-cheek. There is also strong experimental evidence in favor of the conjecture. He wrote, "From the fact that we have not been invaded by hordes of tourists from the future." He later turned this into something more dramatic. On June 28, 2009, a Sunday, Hawking held a cocktail party at Gonville and Caius College, Cambridge. There was a banner reading, "Welcome time travelers." There was champagne. There were hors d'oeuvres. The invitations included the exact coordinates in space and the exact time of the event, and the invitations were only sent after the party had already taken place. The idea was simple. If time travel to the past is possible, and if the coordinates of this party eventually become known to future civilizations, then someone should show up. Future time travelers would know exactly where and when to be. Hawking sat there for a long time. No one came. It was partly a stunt, filmed for his television series, but it was also, in its way, a genuine experiment. Not rigorous, obviously. There are many reasons a future time traveler might skip a Cambridge cocktail party, even if time travel were possible. Maybe the coordinates were lost. Maybe, as several physicists have noted, most CTC proposals only allow you to travel back to the moment the time machine was first created, which would mean no future traveler could reach June 28, 2009. unless a time machine already existed at that date. Hawking's party was testing a very specific version of time travel, the version where an unrestricted visitor from any point in the future can appear at any point in the past. Most physicists would not expect even real CTCs to permit that, but the image is unforgettable. The most famous physicist since Einstein, alone in a room full of champagne and party decorations, waiting for visitors from the future who never arrive. A win-win scenario, Hawking noted. If someone showed up, time travel is confirmed and Hawking gets stock tips. If no one shows up, it supports the chronology protection conjecture. But the conjecture has a problem, a serious one. The C classical calculation that supports it, the one showing divergent energy at the chronology horizon, breaks down precisely where it matters most. The calculation works well at low energies and large scales. But as you approach the chronology horizon, the energies involved climb toward the Planck scale, roughly 10 to the 19th giga-electron volts, corresponding to the Planck time of roughly 10 to the negative 43 seconds. At those scales, the semi-classical approximation is not valid. You cannot trust classical spacetime combined with quantum fields when the energies are high enough to make spacetime itself quantum mechanical. To know what actually happens at the chronology horizon, you would need a complete, self-consistent theory of quantum gravity, a theory that unifies general relativity and quantum mechanics into a single framework. We do not have one. String theory, the leading candidate, has some things to say about chronology protection. Several arguments within string theory lean in Hawking's direction, suggesting that CTCs are indeed forbidden. But string theory is not complete. It is not experimentally confirmed. It may not even be correct. Loop quantum gravity, the other major approach, has its own partial results, but nothing conclusive. Neither program has settled the question, and there are reasons to worry that Hawking was wrong. Some subsequent work found CTC spacetimes where the vacuum fluctuation energy does not diverge outside the chronology horizon. The energy remains finite right up to the boundary. If that is the case in general, then Hawking's proposed mechanism does not work. A time machine does not necessarily destroy itself. Hawking himself acknowledged the limitations. The chronology protection conjecture is, in his own words, a conjecture, not a theorem. 25 years of Hawking's own fame have led many people to believe he proved time travel is impossible. He did not. He proposed that it might be impossible, offered suggestive but incomplete arguments, and then honestly labeled the result as unproven. The fact that it remains unproven as of 2025 is not a minor caveat. It is the entire point. What Hawking was proposing, in the deepest sense, was faith. Educated faith. Faith supported by elegant arguments and compelling calculations. But faith nonetheless. He believed the universe protects chronology. He could not prove it. And the gap between belief and proof is precisely where physics lives. Faith closes questions. Proof closes them permanently. Hawking offered the first. Nobody has provided the second. Where does this leave us? The mathematics of general relativity produces closed time-like curves in solution after solution. Godel's rotating universe, Van Stockham's cylinder, Kerr's rotating black hole, Tipler's infinite cylinder, Gott's cosmic strings, Thorne's wormhole, The equations keep saying yes. Hawking proposed that quantum effects say no, that the universe has a built-in protection mechanism that prevents CTCs from forming. His arguments are suggestive, but not conclusive. They break down at the exact energy scale where the answer lives. The conjecture has never been proven. The final verdict depends on a theory of quantum gravity that does not yet exist, which means the question, is time travel actually forbidden by physics, remains genuinely, stubbornly, uncomfortably open. And if it is open, if the prohibition has not been established, then we need to confront something most people assume has already been dealt with: the paradoxes. Because if the universe does not forbid closed time-like curves, and if the math keeps producing them, then what happens when you go back and try to prevent your own birth? The grandfather paradox is probably the most famous thought experiment in all of popular physics. You travel to the past. You kill your grandfather before he meets your grandmother. Your parent is never born. You are never born. You never travel to the past. Your grandfather lives. Your parent is born. You are born. You travel to the past and kill your grandfather. Round and round. A logical contradiction with no resolution. The classic formulation involves your grandfather, but physicists have proposed sharper versions. Thorne preferred the matricide paradox, killing your own mother before she gives birth to you. Novikov proposed the most direct version, traveling back and killing your younger self. And the standard response from popular culture is that this paradox proves time travel is impossible. If traveling to the past creates logical contradictions, then traveling to the past must be forbidden. This is wrong, and it is wrong in a way that reveals something unexpected about the nature of physics itself. The first rigorous resolution came from Igor Novikov, a Russian physicist based at Moscow State University and the Lebedev Physical Institute. Novikov had been thinking about closed time-like curves since the early 1980s, and in his 1989 book The River of Time, he laid out what would become known as the Novikov self-consistency principle. In 1990, a formal version was published in Physical Review D by a team that included Novikov, John Friedman, Michael Morris, Fernando Echeverria, Gunnar Klinkhammer, Kip Thorne, and Alvi Yurtseva. The paper was titled Cauchy Problem in Spacetimes with Closed Time-like Curves, and it appeared in Volume 42, pages 1915 through 1930. The principle is deceptively simple. The only solutions to the laws of physics that can occur locally in spacetimes containing closed time-like curves are those which are globally self-consistent. What that means in practice is this: you can travel to the past, but you cannot change it. Everything you do in the past was always part of the timeline. If you remember your grandfather telling you a story about a strange visitor he once met, and then you travel to the past and meet your grandfather, you were always that visitor. The encounter already happened. It was always part of the history. You did not change anything. You fulfilled what was already true. And if you try to kill your grandfather, something will prevent you. Your gun jams. You slip on a puddle. You find you cannot pull the trigger. You are hit by a car on the way to his house, not because of some mystical force, but because the only physically realizable solutions are the self-consistent ones. The probability of any event that would create a paradox is exactly zero. This sounds like a cheat. It sounds like the universe is conspiring to prevent paradoxes, which feels just as science fictional as time travel itself. But Novikov and Thorne were not proposing a mystical conspiracy. They were proposing a mathematical constraint. And the mathematics was tested by a paradox so clean, so free of philosophical baggage, that it forced the issue into the open. The paradox came from Joseph Polchinski. In the early 1990s, Polchinski was a physicist who would later become one of the most important figures in string theory. But at this point, he was thinking about something much simpler. He sent a letter to Kip Thorne, proposing the following scenario. Take a billiard ball, fire it into the mouth of a wormhole time machine at precisely the right angle. The ball exits the other mouth in the past and collides with its younger self. The collision knocks the younger ball off course, preventing it from entering the wormhole. But if it never enters the wormhole, it never comes back to deliver the collision. So it does enter the wormhole and comes back and knocks itself off course and does not enter the wormhole. This is the grandfather paradox, stripped of all human drama. No free will, no moral choice, no metaphysics, just a billiard ball, a wormhole, and classical mechanics. The question is not whether you would choose to kill your grandfather. The question is whether a billiard ball can be on a trajectory that makes it knock itself off that trajectory. Pure physics. Thorne called it Polchinski's paradox and assigned it to two of his graduate students at Caltech, Fernando Echeverria and Gunnar Klinkhammer. Their job was to determine whether a self-consistent solution existed. Could the billiard ball enter the wormhole, come back in time, interact with its younger self, and still be on a trajectory that is consistent with all the known laws of physics? Think about what Thorne was asking his graduate students to do. He was asking them to solve a problem that most people would say proves time travel is impossible. He was asking them to find the loophole in the grandfather paradox for a billiard ball, using nothing but Newtonian mechanics and the geometry of a wormhole spacetime. If they failed, if no self-consistent solution existed, it would be strong evidence that CTCs are physically forbidden. If they succeeded, it would mean the most famous argument against time travel does not work. The answer they found stunned everyone. Not only did a self-consistent solution exist, but they found infinitely many of them. For every initial trajectory of the billiard ball, there were an infinite number of self-consistent continuations. The ball from the future does not hit its younger self head-on. It delivers a glancing blow. The glancing blow changes the younger ball's trajectory slightly, just enough to send it into the wormhole at a different angle. It exits in the past at the right angle to deliver exactly that glancing blow. A perfect, self-consistent loop. No paradox, no contradiction. And there were infinitely many different versions of this, different angles of glancing blow, different deflections, all self-consistent, all satisfying every law of physics. The problem was not that there were too few solutions. The problem was that there were too many. Classical physics alone could not determine which self-consistent solution would actually occur. Given a particular initial trajectory, which of the infinitely many consistent outcomes does the universe choose? Thorne and Klinkhammer proposed an answer. Use quantum mechanics. The path integral formulation of quantum mechanics, originally developed by Richard Feynman, says that a particle does not follow a single path. It follows all possible paths simultaneously, and the probability of any particular outcome is determined by the sum over all paths, weighted by a phase factor. Apply this to the billiard ball, and each of the infinitely many self-consistent classical solutions gets a well-defined quantum probability. The universe does not need to choose. Quantum mechanics assigns probabilities to all consistent outcomes. The paradoxical outcome, the direct hit that prevents the ball from entering the wormhole, is not among the consistent solutions. Its probability is 0. This was a profound result. The Novikov self-consistency principle, far from being an ad hoc philosophical dodge, turned out to have deep support in the mathematical structure of classical and quantum mechanics. Self-consistent solutions exist. They are abundant, and quantum mechanics provides a natural mechanism for selecting among them. But Novikov's resolution comes at a price, and the price bothers some physicists deeply. It means the past is immutable. You can visit it. You cannot change it. Your actions in the past were always part of the history. This is sometimes called the banana peel principle. The idea that if you try to create a paradox, some physical event, a slipped foot, a jammed mechanism, a slight miscalculation will always intervene to maintain consistency. The universe is not conspiring. It is simply the case that inconsistent solutions do not exist as valid physical trajectories. David Deutsch proposed a different resolution entirely. Deutsch, an Oxford physicist and one of the founders of quantum computing, is the kind of thinker who does not flinch from conclusions that most people would find intolerable. He is a committed Everettian, a believer in the many worlds interpretation of quantum mechanics, and his resolution of the grandfather paradox only makes sense if you accept that parallel universes are real. He published a paper in 1991 in Physical Review D titled Quantum Mechanics Near Closed Timelike Lines. Instead of analyzing CTCs through space-time geometry, Deutsch approached them through quantum information theory, and his resolution of the grandfather paradox is stranger than the paradox itself. In Deutsch's model, the time traveler exists with probability 1/2. If she is born, she goes back and kills her grandfather. Therefore, she is not born. Therefore, she does not go back. Therefore, her grandfather lives. Therefore, she is born. In Deutsch's quantum framework, both outcomes are superposed. The time traveler exists and does not exist with equal probability. The state is self-consistent because quantum mechanics allows superpositions. But this only works if you accept the many worlds interpretation of quantum mechanics. In Deutsch's model, the time traveler does not return to her own past. She returns to a parallel branch of the multiverse. She kills her grandfather in a different timeline. In her original timeline, her grandfather is alive and well. There is no paradox because there is no single timeline. There are many. The implications for computation are extraordinary. Deutsch showed, and Scott Aronson and John Watrous later proved rigorously, that a computer with access to even a single closed time-like curve could solve problems in the complexity class PSPAS. That class includes all NP-complete problems and vastly more. With a CTC, a quantum computer gains no additional power over a classical computer. Both become equally powerful. A single bit traveling around a closed time-like curve, used repeatedly, could solve problems that no conventional computer could touch in the lifetime of the universe. Aronson and Watrous proved that PCTC, the class of problems solvable in polynomial time with access to CTCs, equals PSPAC. David Bacon showed in 2003 that a single CTC bit cycled repeatedly suffices to solve NP-complete problems. The computational power of time travel is, in a very precise mathematical sense, nearly unlimited. To put that in perspective, NP-complete problems include things like the traveling salesman problem, protein folding, and optimal scheduling. These are problems where checking a solution is easy, but finding the solution in the first place seems to require exponential time. Every major technology company on Earth would pay essentially any price for a reliable way to solve NP-complete problems in polynomial time. A single bit of information traveling around a closed Timelike curve, used cleverly, could do it. The connection between time travel and computation is not a metaphor. It is a theorem. Deutsch offered an analogy for the philosophical strangeness of this. Imagine someone from the present travels back to Elizabethan England with a complete copy of Shakespeare's works and dictates them to Shakespeare. Shakespeare writes them down. They are published. They survive to the present day. The time traveler reads them, takes them back, and dictates them to Shakespeare. Where did the plays come from? Who composed them? Nobody. They exist in a self-consistent loop with no origin. Information created from nothing. The plays are real. They have structure, beauty, depth, but no creative act produced them. They emerged from the loop itself. This is called a bootstrap paradox, or sometimes a causal loop. Unlike the grandfather paradox, it involves no logical contradiction. It is self-consistent, but it violates something that feels fundamental. We expect effects to have causes. We expect information to originate somewhere. In a universe with closed time-like curves, that expectation may be wrong. This is not a flaw in the model. It is a feature, and it is deeply unsettling. Seth Lloyd at MIT proposed a third resolution in 2011, one that is physically distinct from both Novikov and Deutsch. Lloyd's model, called post-selected closed time-like curves, or PCTCs, uses the quantum mechanics of teleportation and post-selection. The post-selection part is crucial. In quantum mechanics, post-selection means keeping only the experimental runs that produce a particular outcome. It is a standard technique in quantum optics labs. Lloyd's insight was that CTCs effectively post-select for self-consistent outcomes. The universe, in this model, only permits the outcomes that do not create paradoxes. Paradoxical outcomes are not prevented by some mechanism. They simply have zero probability of occurring. Lloyd and his collaborators published 2 papers, one in Physical Review D and one in Physical Review Letters, both in 2011. They even performed an experimental demonstration using photonic systems, sending photons through optical circuits that simulated post-selected CTCs. The photons behaved consistently with the PCTC predictions. No paradoxes, every outcome self-consistent. Lloyd's model gives slightly different computational power than Deutsch's. PCTCs give the complexity class PP, probabilistic polynomial time, which is slightly less powerful than P space P, but still far beyond anything achievable without time travel. When asked which model is correct, Lloyd said something that captures the state of the field perfectly. I have no idea which model is really right. Probably both of them are wrong. So where does this leave the grandfather paradox? It leaves it resolved 3 times over by 3 independent approaches using 3 different mathematical frameworks. Novikov says the past is immutable and self-consistency is enforced by physics. Deutsch says you travel to a parallel timeline and there is no paradox because it is not your past. Lloyd says paradoxical outcomes have 0 probability and only consistent outcomes occur. All 3 are internally consistent. All three are mathematically rigorous. None of them has been experimentally distinguished from the others for full-scale CTCs, because we have never observed a full-scale CTC. The grandfather paradox does not forbid time travel. It has been solved so many times by so many people in so many ways that it is no longer the interesting question. The interesting question was always the physics. Can closed time-like curves actually form? Does the universe have a mechanism that prevents them? Is Hawking's conjecture right? And every resolution of the grandfather paradox makes the central question more urgent, not less, because each resolution removes one potential reason to dismiss CTCs. If the paradoxes cannot stop them, and the energy conditions have not been proven to stop them, and Hawking's conjecture remains unproven, then the question of whether time travel is forbidden by physics is more open than most people realize. Each resolution also introduces its own form of strangeness. Novikov gives us an immutable past where free will, at minimum, operates under constraints that have no precedent in our experience. You can visit yesterday. You can watch yourself eat breakfast, but you cannot knock the cereal out of your own hand. Something will stop you. The laws of physics will conspire, not through magical intervention, but through the sheer mathematical fact that no self-consistent solution exists in which you succeed. Deutsch gives us a multiverse where you can kill your grandfather, but only in someone else's timeline, and where the computational consequences are so extreme that a single looping bit solves problems we consider intractable. Lloyd gives us post-selection, a universe that edits its own outcomes to enforce consistency, which sounds dangerously close to a universe with preferences about what is allowed to happen. 3 resolutions, 3 different kinds of strangeness, and all 3 agree on one thing. The grandfather paradox does not prevent time travel. The paradoxes do not save us from time travel. They complicate it. They make it weirder, but they do not make it impossible. And if the paradoxes cannot make it impossible, and Hawking cannot prove it impossible, and the math of general relativity keeps producing it, then we are left exactly where the physics leaves us, with a question that refuses to close. Let us take stock. We started with a birthday present, a 4-page paper from a logician to a physicist, proving that the physicist's own equations permit time travel. From there, we followed the trail. We watched closed time-like curves appear in solution after solution of Einstein's field equations. We watched Kip Thorne turn a science fiction novelist's question into a blueprint for a wormhole time machine. We watched Stephen Hawking try to close the door on time travel and fail. We watched the grandfather paradox, the objection that everyone thinks is fatal, get resolved so many times by so many methods that it stopped being the interesting problem. And now, after all of that, we have to ask what we actually know. The scorecard, as it stands, looks something like this. The mathematics of general relativity says yes. Closed time-like curves are valid solutions. They appear in rotating universes, around spinning cylinders, inside rotating black holes, between moving cosmic strings, through traversable wormholes. The equations have been saying yes since 1924, when Lanczos first stumbled on rotating solutions, and they have not stopped. Every decade produces new CTC solutions. The paradoxes say maybe. The grandfather paradox, the most famous objection, has been resolved 3 independent times by 3 independent methods. Novikov's self-consistency principle, Deutsch's many worlds quantum model, Lloyd's post-selected teleportation model, All three are internally consistent. All three are mathematically rigorous. The paradoxes do not forbid time travel. They constrain it in different, fascinating, deeply strange ways. The energy conditions say probably not. Every practical CTC proposal requires either exotic matter in quantities that dwarf anything achievable, or cosmic scale structures of infinite extent, or the interiors of black holes that are probably destroyed by their own instabilities. The gap between what the math permits and what nature provides is enormous. But enormous is not infinite. Probably not is not no. And Hawking says no. But he could not prove it. The chronology protection conjecture remains exactly that, a conjecture, unproven, dependent on a theory of quantum gravity that does not exist. Hawking's semi-classical arguments break down at the Planck scale, which is precisely where the answer lives. 4 answers, 4 different verdicts, and none of them is final. Each one, examined closely, turns out to depend on something we do not yet know. The mathematical yes depends on whether general relativity is the complete theory of space-time. It almost certainly is not. The paradox resolution depends on which model of quantum mechanics is correct. We do not know. The energy condition objection depends on whether exotic matter in macroscopic quantities is truly impossible. We cannot prove it. The Hawking conjecture depends on what happens at the Planck scale. We have no idea. Every trail leads to the same vanishing point. Quantum gravity, the theory that unifies general relativity and quantum mechanics into a single framework. The theory that would tell us definitively whether the structure of space-time at the most fundamental level permits or forbids closed time-like curves. The theory that does not exist. So where does a physicist go from here? The honest answer is that there is nowhere to go. Not yet. The question of whether closed time-like curves can physically form is a question about quantum gravity. It sits in the gap between general relativity, which says space-time is smooth and curved, and quantum mechanics, which says everything at small enough scales is discrete and probabilistic. Closed time-like curves are a feature of the smooth, curved space-time of general relativity. Whether they survive the transition to a quantum theory of gravity is the question. And we do not have a quantum theory of gravity. This is worth saying plainly, because it can be easy to forget how unusual the situation is. Physics has 2 spectacularly successful theories. General relativity describes gravity and the large-scale structure of space-time. Quantum mechanics and quantum field theory describe every other force and every particle. Both theories are tested to extraordinary precision. General relativity predicts the perihelion precession of Mercury to within 1 part in 10 million. Quantum electrodynamics predicts the magnetic moment of the electron to 11 decimal places. These are the 2 most successful theories in the history of science, and they are incompatible. Not subtly, not at the edges, fundamentally. General relativity assumes space-time is a smooth, continuous manifold that curves in response to mass and energy. Quantum mechanics assumes that physical quantities come in discrete packets and are subject to uncertainty relations. When you try to combine them, when you try to write a quantum theory of the gravitational field, the mathematics produces infinities that cannot be removed. The standard technique for handling infinities in quantum field theory, a procedure called renormalization, does not work for gravity. The theory is non-renormalizable. The infinities keep multiplying. The calculations become meaningless. Every major question about the deep structure of space-time, the nature of black hole singularities, the origin of the Big Bang, the fate of information that falls into a black hole, and the question of whether closed time-like curves can form, runs headlong into this incompatibility. The answer to each of these questions lives in the regime where both quantum mechanics and general relativity matter, and we do not know how to do physics in that regime. This is not a minor gap. This is the central unsolved problem of theoretical physics. It has been the central unsolved problem for nearly a century. Einstein spent the last 30 years of his life trying to bridge it. He failed. Hundreds of physicists have attempted it since. They have made progress. They have built extraordinary mathematical structures, but they have not solved it, and the question of closed time-like curves is hostage to this failure. Consider what this means for our question. General relativity, by itself, permits CTCs. That is established. Quantum field theory on curved spacetime, the semi-classical approximation, suggests that vacuum fluctuations might prevent CTCs from forming. That is Hawking's argument. But the semi-classical approximation is not the final word, because it breaks down precisely where it would need to work. The final word belongs to quantum gravity, and quantum gravity has not spoken. It is like watching two lawyers argue a case where the judge has not yet arrived. One lawyer presents compelling evidence that the defendant is guilty. General relativity, Your Honor, emits closed time-like curves. The equations are clear. The solutions are valid. Every attempt to forbid them has failed. The other presents compelling evidence of innocence. The energy requirements are prohibitive. The semi-classical calculation suggests divergent back reaction. No time traveler has ever been observed. No CTC has ever been detected. Both arguments are internally coherent. Both marshal real facts. But the verdict depends on a judge who does not yet exist. A theory that has not been written. Mathematics that has not been discovered. We are waiting for a judge who may not arrive in our lifetimes. String theory is the most developed attempt to build a quantum theory of gravity. In string theory, the fundamental objects are not point particles, but tiny vibrating strings, and the different modes of vibration correspond to different particles, including the graviton, the hypothetical quantum of gravity. String theory is mathematically rich, internally consistent as far as anyone has been able to tell, and has produced deep insights into the relationship between gravity and quantum mechanics. Several arguments within string theory lean toward chronology protection. Certain string theory solutions that appear to contain CTCs turn out to be unstable or unphysical when examined carefully. This is suggestive, but string theory is not complete. It exists in multiple versions, 5 at last count, that are believed to be different limits of a single underlying theory, sometimes called M theory. But M theory itself has never been fully formulated. Nobody can write down the fundamental equations of M theory. Nobody knows what the theory actually is at a fundamental level. We have approximations, limits, dualities, correspondences, but not the thing itself. And string theory has not produced a single experimental prediction that has been confirmed. The energies required to probe string-scale physics are so far beyond current technology that direct experimental tests may be impossible for centuries, if they are possible at all. String theory may be correct. It may not. We do not know. Loop quantum gravity, the other major approach, takes a different path. Instead of adding new ingredients like strings, it attempts to quantize general relativity directly. Space, in loop quantum gravity, is not continuous. It is made of discrete quanta, tiny loops of gravitational field that weave together into a structure called a spin network. Space at the smallest scale is granular, like fabric. Loop quantum gravity has its own partial results regarding CTCs, and some of them are intriguing, but the theory is also incomplete. It has difficulty reproducing the smooth spacetime of general relativity at large scales, and it has not been experimentally tested either. Neither string theory nor loop quantum gravity can currently answer the question. Both are works in progress. Both may contain the answer. Neither has delivered it. But while the full theory of quantum gravity remains out of reach, something remarkable happened in 2017. 3 physicists, Ping Gao at Harvard, Daniel Jafferis at Harvard, and Erin Wall at Stanford, published a paper that changed the landscape of traversable wormhole physics. They found a new kind of traversable wormhole, and this one did not require anyone to insert exotic matter into the wormhole throat. The context is important. By 2017, the study of wormholes had become entangled, if you will pardon the pun, with one of the deepest problems in physics, the black hole information paradox. When matter falls into a black hole, what happens to the information it carried? Quantum mechanics says information cannot be destroyed. General relativity says the interior of a black hole is cut off from the exterior forever. These two statements cannot both be true. The information paradox has driven decades of research into the relationship between gravity, quantum mechanics, and information. And it was in this context, while studying how information might escape from black holes, that Gao, Jafferis, and Wall discovered their traversable wormhole. The Gao-Jafferis-Wall wormhole works differently from the Morris-Thorne wormhole. Instead of propping the throat open with exotic matter from inside, it uses quantum entanglement between the 2 black holes that form the wormhole's mouths. The entanglement generates a special kind of interaction between the 2 sides, and this interaction, mediated from outside the wormhole, produces the negative energy needed to hold the throat open. The exotic matter is not inserted. It is created by quantum correlations between the 2 ends. To be precise about what this means, the Gao-Jafferis-Wall construction requires a coupling, a direct interaction between degrees of freedom on the 2 boundaries of the wormhole. In the language of the ADS/CFT correspondence, the mathematical framework in which this result was derived, the 2 sides of the wormhole correspond to 2 separate quantum systems that are entangled with each other. When you turn on a coupling between these 2 systems, the entanglement generates a negative energy shockwave that props the wormhole open just long enough for a signal to pass through. The wormhole opens, a message goes through, and the wormhole closes again. It is brief, it is microscopic, but it is traversable. And it does not require anyone to manufacture exotic matter and insert it by hand. This is a fundamentally different construction. The Morris-Thorne wormhole was a piece of science fiction engineering. You needed to find or manufacture exotic matter and physically place it in the wormhole. Nobody knew how to do that. The Gao-Jafferis-Wall wormhole emerges from quantum mechanics itself. The entanglement between the 2 black holes is sufficient. An entanglement is not exotic. It is one of the most well-established features of quantum mechanics. Every pair of entangled particles shares it. The connection to the broader physics is profound. The Gao-Jeffreys wall wormhole is intimately related to a conjecture proposed by Juan Maldacena and Leonard Susskind in 2013 called ER equals EPR. ER refers to Einstein-Rosen bridges, the non-traversable wormholes first described by Einstein and Rosen in 1935. EPR refers to the Einstein-Podolsky-Rosen paradox, the thought experiment about quantum entanglement that Einstein, Podolsky, and Rosen published that same year. The ER equals EPR conjecture proposes that these two phenomena, wormholes and entanglement, are the same thing. Every pair of entangled particles is connected by a tiny, non-traversable wormhole, and every wormhole is a manifestation of entanglement between the regions it connects. If ER equals EPR is correct, then wormholes are not exotic objects. They are everywhere. Every entangled pair of particles in the universe, and there are unimaginably many, is connected by a microscopic Einstein-Rosen bridge. The fabric of spacetime itself may be stitched together by entanglement, with wormholes forming the threads. This idea, developed by Mark van Ramsdonk and others, suggests that spacetime and entanglement are two descriptions of the same underlying structure. Destroy the entanglement and you destroy the spacetime. The geometry of the universe is in some deep sense built from quantum information. There is something almost poetic about this. Einstein spent the second half of his career trying to reduce physics to geometry. He wanted to show that particles and forces are manifestations of spacetime curvature, that geometry is fundamental, and everything else is derived. Now, 70 years after his death, the leading edge of theoretical physics is suggesting something even stranger. Spacetime itself may not be fundamental. It may emerge from quantum entanglement. The geometry Einstein worshipped may be a projection of something deeper, something informational, something quantum. If that is right, then the question of whether wormholes can be traversable, whether closed time-like curves can form, is ultimately a question about quantum information, about what kinds of entanglement structures are physically possible, about the quantum rules that govern how information can be distributed across a system. And that brings us full circle in a way. Godel's incompleteness theorems were about the limits of formal systems. What can a system prove about itself? What truths lie beyond its reach? The question of CTCs may be the physics version of the same problem. What can the laws of physics prove about the structure of time? What possibilities lie beyond their ability to forbid? None of this proves that traversable wormholes suitable for time travel can be built. The Gao-Jeffreys wall wormhole is traversable, but it is tiny, submicroscopic, and the message that can pass through it is extremely limited. It is closer to a proof of concept than a blueprint. And the step from a few qubits of information can traverse a microscopic wormhole to a human being can walk through a macroscopic wormhole and arrive in the past is a step of such staggering magnitude that it may never be taken, but the direction of progress is notable. In 1988, Thorne's wormhole required exotic matter that nobody knew how to produce. In 2017, Gao, Jeffreys, and Wall showed that entanglement could substitute for exotic matter. The requirement became less impossible, not possible, certainly not practical, but less impossible. The goalpost moved. There is an important caveat here. The fact that the goalpost moved does not mean it will keep moving. Science is not a story of inevitable progress toward a predetermined conclusion. It is entirely possible that the goalpost will move back. That future work in quantum gravity will show that the Gauss-Jeffreys wall mechanism does not scale, that traversable wormholes are forbidden at macroscopic scales, that chronology protection is rigorously enforced by whatever the correct theory turns out to be. Many physicists expect exactly this. Kip Thorne himself eventually concluded that time machines probably self-destruct, though he could not prove it. The weight of intuition among working physicists leans toward chronology protection. But intuition is not a theorem, and the history of physics is littered with confident intuitions that turned out to be wrong. And so the deepest version of the question comes into focus. Is the prohibition against closed time-like curves a problem of engineering or a problem of principle? If it is engineering, then we simply lack the technology. A sufficiently advanced civilization, given enough energy and enough understanding of quantum gravity, could build a time machine. The obstacle is practical, not fundamental. We are in the position of a medieval blacksmith told about nuclear reactors. The physics permits it. We just cannot do it yet. If it is a problem of principle, then the laws of physics contain a fundamental prohibition, something deeper than engineering, deeper than energy conditions, deeper than Hawking's conjecture, something that says at the most fundamental level that closed, time-like curves cannot form. Not because we lack the exotic matter, not because the energy density diverges, but because the correct theory of quantum gravity, whatever it turns out to be, simply does not allow it. The way thermodynamics does not allow perpetual motion machines. The way quantum mechanics does not allow simultaneous precise measurement of position and momentum. A law of nature, not a lack of cleverness. Nobody knows which it is. That is the truth. Not, we think it is probably forbidden. Not, the evidence suggests it is impossible. Nobody knows. The greatest minds in theoretical physics have spent the better part of a century trying to answer this question, and they have not succeeded. The question remains open because the physics required to close it does not yet exist. There is a third possibility, and it is perhaps the most unsettling of all. It may be that the question itself is ill-posed, that asking whether CTCs are forbidden or permitted assumes a kind of binary that the actual theory of quantum gravity does not respect. Perhaps, in the correct theory, CTCs are neither forbidden nor permitted, but something else entirely. Perhaps the notion of a classical spacetime with smooth, closed, time-like curves is an approximation that simply does not apply in the quantum regime. The way asking, which slit did the electron go through, is ill-posed in quantum mechanics, not because the answer is unknown, but because the question assumes something, a definite trajectory that does not exist. If quantum gravity similarly undermines the classical notion of a space-time path, then the question of whether that path can close into a loop may dissolve rather than be answered. Some physicists suspect this is what will happen, that the resolution will not be CTCs are allowed or CTCs are forbidden, but the concept of a CTC does not survive quantization. The smooth, continuous world lines of general relativity may turn out to be approximations that work well in ordinary conditions but become meaningless at the Planck scale. The way temperature is a meaningful concept for a gas, but meaningless for a single molecule. If closed time-like curves are an artifact of the classical approximation, then the question of their physical reality is moot. They are neither forbidden nor committed. They are an artifact of a description that does not apply, but this is speculation. We do not know if quantum gravity dissolves the question or answers it. We do not know if the resolution is yes, no, or does not apply. We know only that the question, in its current form, cannot be settled with current physics. This would be a clean place to end. The question is open. The answer awaits quantum gravity. Physics continues. But there is one more thread to close, and it leads back to where we started. After Einstein died on April 18, 1955, Godel withdrew. The daily walks ended. The one person who operated at Godel's altitude, who could follow his reasoning, challenge his conclusions, and keep him tethered to something resembling normal human life, was gone. Godel continued working. He continued thinking, but his world contracted. The paranoia that had haunted him since Moritz Schlick's murder in 1936 deepened. His fear of poisoning, always present, became increasingly dominant. His social circle, never wide, narrowed to almost nothing. He corresponded with a few mathematicians. He attended some faculty meetings, but the walks were over, and without them, without Einstein's warmth and humor and stubborn rationality as a daily counterweight, Godel's eccentricities hardened into something closer to illness. He received honors. He was awarded the National Medal of Science in 1974. He was elected to the Royal Society. His incompleteness theorems were recognized as among the greatest intellectual achievements of the century. But none of this penetrated the shrinking perimeter of his life. The world's accolades could not substitute for one daily conversation with a man who understood him. His diet narrowed. In his later years, according to accounts in The New Yorker and multiple biographies, he subsisted largely on butter, baby food, and laxatives. He was already thin. He became gaunt. Photographs from his last decade show a man being slowly erased, the physical form diminishing as the mental architecture remained intact. And through all of it, the one constant was Adele. She prepared his food. She tasted it before he would eat. She was the single filter between Godel and his conviction that the world was trying to poison him. Without her, the filter did not exist. Without her, he would not eat. In late 1977, Adele suffered a stroke. She was hospitalized. For the first time in decades, Godel was alone with his food and his fear. He refused to eat. Friends and colleagues tried to intervene. They brought food. They tried to reason with him. But Godel's logic, the same implacable logic that had shattered the foundations of mathematics at 25 and proven time travel possible at 43, was now turned against his own survival. The food might be poisoned. He could not verify that it was safe. Therefore, he would not eat. The argument was airtight if you accepted the premise, and Godel, trapped inside his own mind, could not reject the premise. On January 14, 1978, Kurt Godel died at Princeton Hospital. He was 71 years old. He weighed 29 kilograms, 65 pounds. The death certificate listed the cause as malnutrition and inanition caused by personality disturbance. The greatest logician since Aristotle, the man who broke mathematics and bent time, starved himself to death because the one person he trusted to taste his food was in a hospital bed and could not reach him. Adele survived. She recovered from the stroke and lived until 1981, 3 more years. If she had not been hospitalized, If the stroke had come a year later, if Godel had been able to hold on, he might have lived. The logic that killed him was not faulty. Given his premises, his conclusion was airtight. The tragedy was in the premises. The tragedy was that a mind capable of seeing the deepest structures of mathematics and space-time could not see past a fear that any doctor could have named, but none could have cured. There is an irony here that Godel himself might have appreciated, though it is the kind of irony that is difficult to look at directly. Godel spent the central years of his intellectual life arguing that time is not real, that the flow of time, the sense that the past is gone and the future has not yet arrived, is an illusion, that past, present, and future coexist in a static eternal block, that his rotating universe, with its closed time-like curves permitting travel to any point in time, reveals the true nature of reality, that we are trapped in an illusion of sequence when in fact everything is already there. Everything has already happened. Everything is always happening. And yet Godel could not escape his own present. The most brilliant logician of his century, the man who proved that time loops are consistent with the fundamental laws, could not reach backwards to the decades when Einstein was alive and walking beside him, could not reach forward to a future where his fear might have been treated, could not reach sideways to the hospital where Adele lay recovering from a stroke. She would survive. She would survive it. She would live until 1981. But Godel could not wait. He could not eat. He could not trust. He was trapped in the narrow corridor of the present moment, a moment defined by loneliness and hunger, and a fear he could not reason his way past. The man who proved that time travel is mathematically possible died imprisoned in time. The man who showed that the past is not inaccessible, that the laws of physics do not forbid returning to it, could not return to any of the moments that might have saved him. Not to the walks with Einstein, not to Vienna before the war, not even to last week, when Adele was still home and the food was still safe. This is not a metaphor. It is the literal situation. Godel proved that closed time-like curves are consistent with the laws of general relativity. He proved that nothing in the fundamental equations prevents a traveler from visiting their own past. And he died in a present he could not exit, destroyed by a fear that operated entirely within the bounds of logic, but was answerable to nothing beyond it. Einstein's equations permit closed time-like curves. Godel proved it. The proof has never been overturned, but proving that time can loop, and actually looping through it, are separated by a gulf that may be infinite, a gulf made of exotic matter and quantum gravity, and the difference between a mathematical solution and a physical reality. Godel could see across that gulf. He could describe what lay on the other side. He could prove it was there, but he could not cross it. Nobody can. Not yet. And perhaps not ever. The question Godel raised in 1949 remains exactly as he left it. Do the laws of physics forbid closed time-like curves? The equations say no. The universe, so far, says maybe. Hawking said yes, but could not prove it. The paradoxes said nothing useful. And the answer, the real answer, requires a theory we have not yet written. Somewhere in this space between general relativity and quantum mechanics, between the smooth curves of Einstein's space-time and the discrete quanta of the quantum world, the answer is waiting. It has been waiting since 1949. It may wait considerably longer. And until it arrives, the possibility that time travel is permitted by the fundamental laws of physics remains exactly what it has been for 76 years, open, unresolved, refusing to close. Godel would have understood some questions, the most important ones, are not the ones with answers. They are the ones that reveal the boundaries of what we know. His incompleteness theorems showed that mathematics contains true statements it cannot prove. His rotating universe showed that physics contains possibilities it cannot forbid. Both results point in the same direction, toward the limits, toward the edge of the map, toward the place where the most advanced systems of human thought encounter something they cannot resolve, not because the question is poorly posed, but because the system is not yet sufficient. There may even be a deeper parallel. Godel's first incompleteness theorem says that any sufficiently powerful formal system is either incomplete or inconsistent. It contains truths it cannot prove, or it contains contradictions. General relativity, as a formal system for describing space-time, contains closed time-like curves. Are these the equivalent of unprovable truths, genuine features of reality that we cannot yet access? Or are they the equivalent of contradictions, artifacts of a system that is not quite right and will be eliminated by the more complete theory of quantum gravity? Gödel's theorem does not answer this question directly. It is mathematics, not physics, but the structural similarity is striking. A system confronting its own limits, truths that cannot be proven, possibilities that cannot be forbidden. The question of closed, time-like curves is one of those questions. It sits on the boundary between what general relativity allows and what quantum gravity might forbid. It is a question about the deep structure of time, which is a question about the deep structure of reality, which is a question that may require physics we have not yet imagined. And in the meantime, the equations sit there, patient, containing their closed time-like curves the way a map contains an uncharted territory. The territory is on the map. It has been on the map since 1949, but nobody has gone there. Nobody knows if the territory is real, or if the map is wrong, or if the territory exists but is surrounded by walls that no technology could breach. Kurt Godel put it on the map. He did not live to see it explored, and the question he planted in 4 pages of mathematics given as a birthday gift to his best friend remains the question: is time travel forbidden by the laws of physics? We do not know. The greatest logician of the 20th century showed us that the answer might be no. The greatest physicist of the 20th century spent his last years walking home with the man who proved it, and neither of them, nor anyone since, has been able to close the question. It is still 1949 on that map. The rotating universe is still turning. The closed time-like curves are still there, winding through every event in the space-time. And somewhere in Princeton, if you believe in the block universe as Godel did, 2 old men are still walking home together through the quiet streets, arguing about time. They are always walking. They are always arguing. And the question is always open.